there is a place where our solar system simply ends. Not with a wall or a boundary marker, but with a gradual surrender to the infinite cold between stars. Here, 40 times farther from the Sun than Earth, sunlight becomes so thin it's barely distinguishable from starlight. This is the Kuiper Belt, a vast ring of ancient ice and rock that marks the frontier between the familiar physics of planetary motion and the deeper mysteries of interstellar space. It's a realm where objects drift in orbits so wide that a single year lasts centuries, where the familiar dance of seasons becomes a cosmic waltz measured in geological time. Here, Pluto takes 248 Earth years to complete one journey around our star. Here, the gravitational influence of the Sun grows whisper-thin, competing with the subtle pull of nearby stars for dominance over matter that hovers at the very edge of belonging to our cosmic neighbourhood. And it was here, in this twilight realm between worlds, that something impossible happened. On a night when telescopes across the Earth were scanning the outer darkness for the usual suspects, distant comets, wandering asteroids, the occasional chunk of primordial ice knocked loose from the solar system's ancient architecture, astronomers detected an object that shouldn't exist, moving too fast, coming from the wrong direction, following a trajectory that defied every known law of solar system mechanics. They named it 3I Atlas, though at first no one understood why this cosmic visitor would become one of the most significant astronomical discoveries of our time. It appeared to be just another interstellar object, a wandering piece of cosmic debris that had been ejected from some distant star system and happened to pass through our cosmic neighbourhood during its journey through the galaxy. But Atlas was different, and that difference would change everything we thought we knew about what lurks in the darkness at the edge of our solar system. Interstellar objects are cosmic nomads, chunks of rock, ice, or metal that have been gravitationally ejected from their birth systems and now wander the galaxy like messages in bottles thrown into an ocean of space. When they pass through our solar system, they follow what astronomers call hyperbolic trajectories, paths so fast and steep that they make a single sweeping approach toward the Sun before disappearing back into the interstellar void, never to return. The first confirmed interstellar visitor, discovered in 2017 and named Oumuamua, Hawaiian for Scout, behaved exactly as theory predicted. It tumbled through space like a cosmic cigar, reflecting sunlight in a pattern that revealed its elongated shape. It accelerated as it approached the Sun, then decelerated as it climbed back out of the solar system's gravitational well, following the precise mathematical curve that physics demanded. Oumuamua was strange in appearance but predictable in behaviour, a textbook example of how interstellar objects should move through foreign star systems. The second confirmed visitor, designated Borisov, arrived 2 years later and behaved like a familiar comet, developing a glowing tail as solar radiation heated its icy surface, outgassing in precisely the way astronomers expected from a chunk of frozen material approaching an alien sun, different in composition from solar system comets, but utterly conventional in its gravitational dance with our star. Then came Atlas. At first, the calculations looked routine. Initial observations suggested another hyperbolic visitor making its singular passage through the inner solar system. The trajectory seemed to follow the expected path, a steep approach from interstellar space, a sharp turn around the Sun's gravitational influence, and a departure back into the cosmic deep. Atlas appeared to be just the third confirmed interstellar object, interesting for its rarity but not fundamentally challenging to our understanding of cosmic mechanics. But as observations accumulated over weeks and months, something became clear that made astronomers pause at their computer screens and double-check their calculations. Atlas wasn't following the predicted path. Its trajectory showed subtle deviations, small changes in velocity and direction that couldn't be explained by the gravitational influence of any known object in the solar system. These weren't random measurement errors or telescope calibration issues. The deviations were systematic, consistent, and pointed in a specific direction. Something was tugging at Atlas, something massive enough to alter the trajectory of an object moving at interstellar velocities, yet invisible to every telescope and detector humanity had pointed toward that region of space. The mathematics were unsettling. To influence an object moving at the extreme speeds typical of interstellar visitors requires enormous gravitational fields, masses comparable to planets. But there were no planets in that direction, no large asteroids, no known objects of any kind, just empty space at the solar system's edge, where sunlight fades to cosmic background radiation and the familiar laws of planetary motion give way to the deeper silence of intergalactic space. Astronomers began plotting Atlas's deviations with increasing precision, tracking each subtle course correction as the cosmic visitor responded to gravitational influences that shouldn't exist. The pattern that emerged was both elegant and terrifying in its implications. Atlas was being pulled towards something that possessed significant mass, yet remained completely invisible to human observation. This wasn't unprecedented in astronomical history. The planet Neptune was discovered exactly this way in 1846, when astronomers noticed that Uranus wasn't following its predicted orbit. Mathematical analysis of Uranus's orbital deviations revealed the location and mass of an unseen planet, which was subsequently found precisely where the calculations predicted it should be. Hidden gravitational influences had led to the discovery of an entire world, but Atlas's deviations pointed toward a region of space that had been searched repeatedly with increasingly sophisticated instruments. If a planet large enough to influence interstellar objects was lurking in the outer solar system, telescopes should have detected its reflected sunlight by now. The absence of any visible object large enough to account for Atlas's trajectory, changes suggested something far more mysterious than a conventional planet. The cosmic visitor had become an unwitting detective, its path through space serving as a gravitational probe that mapped invisible mass lurking in the darkness beyond Neptune's orbit. Each slight course correction added another data point to a growing map of something that influenced matter without revealing itself to light. Something that bent space without offering any reflection, emission, or thermal signature that human technology could detect. In the deep mathematics of orbital mechanics, a pattern was emerging that connected Atlas's impossible deviations to one of the most profound mysteries in astronomy: the question of what might be hiding in the gravitational shadows at the edge of our solar system. For decades, astronomers had suspected that something massive was influencing the orbits of distant objects, shepherding them into aligned patterns that suggested the presence of an unknown gravitational giant. They had called this hypothetical object Planet 9, imagining a world perhaps 10 times more massive than Earth, following an extremely elongated orbit that kept it perpetually hidden in the outer darkness. Searches had been ongoing for years, scanning the sky for the faint reflection of sunlight that would reveal this hidden world. But telescope after telescope came up empty, finding nothing in the regions where Planet 9 should be visible. Atlas's deviations suggested a disturbing possibility that astronomers had been looking for the wrong kind of object entirely. What if the unseen gravitational influence wasn't a planet that reflected light, but something that consumed light itself? What if the hidden mass shaping the outer solar system's architecture was something that could never be seen, only felt through its gravitational whispers? As Atlas continued its journey through the outer solar system, its trajectory deviations painted an increasingly detailed portrait of invisible mass lurking in the cosmic shadows. The mathematics pointed toward an object with significant gravitational influence yet no observable properties, a presence that shaped space itself while remaining forever hidden from direct detection. The implications were staggering. If Atlas's course corrections were accurate, humanity might be living in a solar system that harbored something far stranger than hidden planets or wandering asteroids. We might be sharing our cosmic neighborhood with an object so fundamentally different from ordinary matter that it existed at the intersection of astronomy and the deepest mysteries of physics itself. Was Atlas simply a cosmic messenger, carrying news of its journey through the interstellar void? Or was it something far more significant, a gravitational probe that had finally revealed the presence of something we had never imagined could exist at the edge of our own solar system? In the patient mathematics of orbital mechanics, where every force leaves its signature in the gentle curves of celestial motion, Atlas was writing a message that challenged everything astronomers thought they knew about what lurks in the darkness beyond the realm of planets and light. Something was pulling at this cosmic visitor from the deep shadows at the solar system's edge. Something massive, something invisible, something that had been waiting in the cosmic silence for a messenger like Atlas to finally reveal its presence to human consciousness, reaching toward the infinite mystery of space, What could possess the mass to influence interstellar objects, yet remain completely hidden from the most sophisticated telescopes ever built? What kind of cosmic architecture could shape the gravitational landscape of our solar system, while offering no reflection, no emission, no signature of its existence except the mathematical whispers of its influence on passing matter? Atlas had come from the deep space between stars, carrying with it the possibility that our solar system harbours secrets far stranger than anyone had dared to imagine. In the deviations of its trajectory lay clues to a mystery that connected the most fundamental physics of the early universe to the hidden architecture of our own cosmic neighbourhood. The stranger at the edge had arrived not just to visit, but to reveal. What it was pointing toward in the darkness beyond Neptune would challenge every assumption about the nature of matter, gravity, and the invisible forces that shape the cosmos from the shadows where light itself cannot reach. Picture yourself standing in the Atacama Desert, where the air is so thin and dry that astronomers have built some of the most powerful telescopes on Earth to peer into the cosmic deep. Here, under skies so clear they seem like windows into eternity, teams of scientists spend their nights hunting for something that has eluded discovery for over a decade. A hidden world lurking somewhere in the darkness beyond Neptune's orbit. They call it Planet 9, and it represents one of the most compelling mysteries in modern astronomy. Not because of what it is, but because of what it does, shaping the architecture of our outer solar system through gravitational influences that operate across distances so vast they challenge human imagination, yet remaining completely invisible to every telescope humanity has pointed toward the cosmic frontier. The mystery began with careful observation of some of the most distant objects in our solar system, chunks of ice and rock that drift in the outer darkness, following orbits so elongated they take thousands of years to complete. These are the extreme trans-Neptunian objects, cosmic wanderers that venture far beyond the realm of familiar planets into regions where the sun becomes just another star in a field of distant lights. Most objects in the outer solar system follow orbits scattered randomly across the sky, their paths shaped by the chaotic gravitational influences of the giant planets and the slow tidal forces of nearby stars. But in the late 20th and early 21st centuries, as telescopes became sophisticated enough to detect these distant wanderers, astronomers noticed something that shouldn't exist, a clustering pattern that defied every expectation about how the outer solar system should behave. 6 of the most distant known objects, Sedna, Biden, the Goblin and others, with designations that sound more like cosmic poetry than scientific nomenclature, all shared remarkably similar orbital characteristics. Their elliptical paths pointed in nearly the same direction, tilted at similar angles to the plane of the solar system, and clustered together in ways that probability theory suggested should be virtually impossible. The chances of this happening randomly were less than 1 in 14,000. Something was shepherding these distant objects into aligned orbits, herding them like a cosmic sheepdog through gravitational influences that operated across billions of miles of empty space. In 2016, 2 astronomers at the California Institute of Technology, Mike Brown, whose previous work had led to Pluto's reclassification as a dwarf planet, and Konstantin Batygin, a specialist in celestial mechanics, published calculations that sent ripples through the astronomical community. Their mathematical models suggested that the orbital clustering could be explained by the gravitational influence of an undiscovered planet roughly 10 times more massive than Earth, following an extremely elongated orbit that kept it perpetually hidden in the outer darkness. This hypothetical world, which they dubbed Planet 9, would orbit the Sun at distances between 200 and 1200 astronomical units, meaning its closest approach would still be 7 times farther from the Sun than Neptune, and its most distant point would carry it nearly 40 times beyond Neptune's orbit into the gravitational borderland between our solar system and interstellar space. The mathematical elegance was compelling. Computer simulations showed that a planet of this size, following this type of orbit, would create exactly the kind of gravitational shepherding observed in the outer solar system. The aligned orbits of distant objects weren't random chance. They were the gravitational fingerprints of an unseen world whose influence shaped the architecture of our cosmic neighbourhood across geological time. But there was a problem. A planet 10 times more massive than Earth, even at the enormous distances suggested by the orbital calculations, should be detectable by modern telescopes. At its closest approach, Planet 9 should reflect enough sunlight to appear as a faint but visible dot against the stellar background. Sophisticated sky surveys using some of the most sensitive instruments ever built should have found it by now. The search began immediately. Teams of astronomers worldwide pointed their telescopes toward the regions of sky, where gravitational modelling suggested Planet 9 should be located. Survey programs scanned millions of stars, looking for the telltale motion that would reveal a planet moving slowly against the background of more distant objects. Infrared telescopes searched for the faint thermal emission that even a cold, distant world should produce. Years passed. Surveys covered larger and larger areas of sky with increasing sensitivity. Telescopes in space, free from atmospheric interference, joined the hunt. Citizen science projects enlisted thousands of volunteers to examine telescope images for signs of planetary motion. Advanced computer algorithms designed to detect the subtle patterns of reflected light that would reveal a hidden world analyzed data from multiple observational campaigns. The searches came up empty, again and again. By 2020, the most comprehensive sky surveys in astronomical history had covered nearly the entire region where Planet 9 should be visible, yet found nothing. If the planet existed and was as large as the gravitational calculation suggested, it should have been detected multiple times over. The absence of any visible object large enough to explain the orbital clustering became as puzzling as the clustering itself. Some astronomers began to wonder whether the orbital patterns might be observational bias, the result of telescopes looking in similar directions and detecting objects that appeared clustered simply because they were easier to find in certain regions of sky. Others suggested that the clustering might be temporary, the result of gravitational perturbations that would eventually scatter the objects into more random orbits. But the gravitational modelling was too precise, the orbital alignments too consistent to dismiss easily. Something with significant mass was influencing the outer solar system's architecture. The mathematical fingerprints were clear, even if the object creating them remained invisible. As search after search failed to find Planet 9, a disturbing possibility began to emerge. What if astronomers had been looking for the wrong kind of object entirely? What if the unseen gravitational influence wasn't a conventional planet that reflected sunlight, but something fundamentally different? Something that could possess enormous mass yet remain completely invisible to every form of electromagnetic observation? The searches had been based on a simple assumption, that massive objects in the solar system would be planets or large asteroids or comets, chunks of rock, ice or gas that would reflect sunlight or emit thermal radiation detectable by telescopes. But what if the hidden object belonged to a completely different category of cosmic architecture? What if it was something that didn't interact with light at all, except through the gravitational distortion of space-time itself? This possibility led to one of the most radical proposals in modern astronomy, that the outer solar system might harbour not a hidden planet, but a primordial black hole, an object with the mass of multiple Earths compressed into a sphere smaller than a city, invisible to all forms of electromagnetic observation, yet capable of creating precisely the gravitational effects observed in the orbits of distant objects. The idea seemed almost too strange to consider seriously. Black holes were exotic objects associated with the death of massive stars or the supermassive engines that power galactic cores, not quiet residents of suburban solar systems. But as the searches for Planet 9 continued to find nothing, and as the orbital clustering of distant objects became more pronounced with additional discoveries, the possibility that something truly exotic might be lurking in the outer darkness became increasingly difficult to dismiss. The mathematical models were clear. Something with significant mass was shaping the outer solar system's gravitational landscape. Whether it was a conventional planet that had somehow evaded detection, or something far stranger that challenged every assumption about what kinds of objects could exist in the cosmic suburbs, the evidence for its existence was written in the patient mathematics of orbital mechanics. And now, with the arrival of Atlas and its inexplicable trajectory deviations, astronomers had a new kind of evidence for invisible mass in the outer solar system. Not just the long-term shepherding of distant objects, but the real-time gravitational influence on a visitor from interstellar space. Atlas was providing a different kind of probe, a cosmic test particle, whose deviations could map the gravitational landscape of the outer solar system with unprecedented precision. The combination was compelling and unsettling. For decades, the orbital clustering of distant objects had suggested something massive was hidden in the outer darkness. Now Atlas was responding to gravitational influences from the same general region of space, providing independent confirmation that significant mass existed where telescopes found only empty sky. The hunt for the invisible had entered a new phase. Whether the hidden object was an exotic planet that had somehow escaped detection, or something far stranger that existed at the intersection of astronomy and the deepest mysteries of physics, its presence was becoming undeniable. The question was no longer whether something massive was lurking in the outer solar system, but what kind of object could possess such gravitational influence while remaining completely invisible to human observation. Atlas had arrived at precisely the right moment to serve as a cosmic messenger, its trajectory deviations providing new clues to a mystery that had frustrated astronomers for over a decade. Whatever was pulling at this interstellar visitor from the darkness beyond Neptune was about to be revealed not through direct observation, but through the mathematical whispers of its gravitational influence on matter passing through its domain. The invisible giant that shaped our solar system's architecture was finally ready to announce its presence, not through reflected light or thermal emission, but through the gentle but unmistakable tug it exerted on cosmic visitors brave enough to venture into the gravitational shadows at the edge of our cosmic neighbourhood. What could possess the mass to influence both distant solar system objects and passing interstellar visitors, yet remain completely hidden from the most sophisticated telescopes ever built? The answer would challenge everything astronomers thought they knew about the kinds of objects that could exist in the quiet suburbs of star systems, and force humanity to confront the possibility that we share our cosmic neighbourhood with something far stranger than hidden planets or wandering asteroids. The hunt for the invisible was about to reveal that the most profound mysteries often hide not in distant galaxies or exotic cosmic phenomena, but in the familiar darkness at the edge of home. In the deepest archives of theoretical physics, where mathematics meets the fundamental architecture of reality, lies one of the most elegant and terrifying concepts in all of science: the primordial black hole, born not from the collapse of dying stars, but from the violent quantum fluctuations that rippled through space-time itself during the first fraction of a second after the Big Bang. These exotic objects represent a direct connection between the cosmic present and the universe's most ancient history. Unlike the stellar black holes that form when massive stars exhaust their nuclear fuel and collapse under their own gravity, primordial black holes emerge from the fundamental structure of space and time itself. In those first infinitesimal moments after creation, when the universe was smaller than a proton and hotter than the cores of all stars combined, tiny regions of space experienced density fluctuations so extreme they collapsed directly into black holes without ever becoming stars or planets or any form of ordinary matter. The mathematics are staggering in their implications. These ancient objects could possess any mass from microscopic to stellar, depending on the exact conditions during their formation. Some would have evaporated almost immediately through Hawking radiation, their tiny masses insufficient to maintain stability across cosmic time. Others, with masses comparable to asteroids or planets, could survive for billions of years, silent, invisible witnesses to the universe's birth, wandering through space as gravitational fossils of creation itself. For decades, primordial black holes remained purely theoretical, elegant solutions to Einstein's equations that described how matter and energy could be compressed beyond the event horizon, where space and time become so distorted that nothing, not even light, can escape. They were mathematical curiosities, cosmic possibilities that existed in the realm of theoretical physics, but had never been detected in the real universe. Then, in 2019, two physicists working at Durham University and the University of Illinois proposed something that sent ripples through both the astronomical and theoretical physics communities. Jakob Schultz and James Unwin published calculations suggesting that a primordial black hole, specifically one with roughly the mass of Earth but compressed to a sphere no larger than an orange, could be responsible for the gravitational effects attributed to the hypothetical planet 9. The proposal was both elegant and unsettling. Instead of a conventional planet hiding in the outer darkness, the mathematical model suggested our solar system might harbour something far more exotic, a region of space where gravity had become so intense that it created a one-way barrier in space-time itself. An object that possessed significant mass yet remained completely invisible because it absorbed all electromagnetic radiation that approached its event horizon. The physics of such an object challenge human intuition. Imagine Earth's entire mass, every mountain, ocean, continent and core, compressed into a sphere smaller than a grapefruit. The gravitational field surrounding such an object would be so intense that time itself would slow down near its surface, and space would be curved so severely that any matter or energy venturing too close would spiral inward along trajectories from which there could be no return. Yet from a distance, this primordial black hole would behave exactly like any other massive object. Its gravitational influence would extend across astronomical distances, capable of shepherding the orbits of distant objects through the same gravitational mechanics that govern planetary motion. The difference would be that instead of reflecting sunlight like a conventional planet, it would absorb every photon that crossed its event horizon, remaining forever invisible to telescopes designed to detect reflected or emitted light. The elegance of the solution was compelling. A primordial black hole with Earth's mass, orbiting at the distances suggested by Planet 9 calculations, would create precisely the gravitational effects observed in the outer solar system. It would shepherd distant objects into aligned orbits through the same gravitational mechanics that conventional planets use to influence their moons and rings. The mathematical models worked perfectly, except that the object creating these effects would be fundamentally undetectable through direct observation. This wasn't science fiction speculation, but rigorous application of well-established physics to astronomical observations. The existence of primordial black holes was a natural consequence of current understanding about the early universe. Their formation mechanisms were understood from first principles of quantum mechanics and general relativity. The only question was whether any had survived the billions of years since cosmic inflation, and whether they might be lurking in observable regions of space. The detection challenge was formidable. Unlike stellar black holes, which often exist in binary systems where they strip matter from companion stars and create observable, high-energy emissions, a primordial black hole wandering alone through space would be completely silent. It would emit no light, produce no heat, and generate no electromagnetic signature that human technology could detect. Its presence could only be inferred through gravitational effects on nearby matter, exactly the kind of indirect evidence that had led to the Planet 9 hypothesis in the first place. But the gravitational signature would be unmistakable. A primordial black hole in the outer solar system would influence passing objects through the same gravitational mechanics that govern all massive bodies, creating orbital perturbations that could be detected and analysed through careful observation of affected objects. The mathematics of its influence would be identical to those of a conventional planet, but the object creating these effects would belong to a completely different category of cosmic architecture. The implications extended far beyond solar system astronomy. If primordial black holes existed in detectable numbers, they could represent a significant component of dark matter, the mysterious substance that makes up roughly 27% of the universe, yet interacts with ordinary matter only through gravitational forces. Dark matter's gravitational effects are observed throughout the cosmos, from the rotation curves of galaxies to the large-scale structure of cosmic web itself, yet its fundamental nature remains one of the deepest mysteries in physics. Primordial black holes offered an elegant solution to the dark matter puzzle. Objects that possessed significant mass, yet remained invisible to electromagnetic observation, distributed throughout the universe as gravitational fossils of cosmic inflation. If such objects existed in sufficient numbers, they could account for the missing mass that astronomers observe through gravitational effects but cannot detect through conventional telescopes. The possibility that our own solar system might harbour one of these exotic objects provided an unprecedented opportunity to study primordial black holes up close. Instead of inferring their properties from statistical analysis of cosmic surveys or gravitational wave detections, astronomers could potentially examine a primordial black hole through direct gravitational observation of its effects on solar system objects. The theoretical framework was sound, the mathematical models were consistent with observations, and the predictions were testable through continued observation of outer solar system dynamics. What remained was confirmation. evidence that would distinguish between a conventional hidden planet and something far more exotic lurking in the gravitational shadows at the edge of our cosmic neighbourhood. The detection methods would need to be indirect, relying on gravitational effects rather than electromagnetic observation. But the techniques already existed, refined through decades of celestial mechanics and orbital analysis. The same mathematical tools used to discover Neptune through its gravitational influence on Uranus could be applied to mapping the gravitational field of a primordial black hole through its effects on passing objects. What made the possibility particularly compelling was the convergence of multiple lines of evidence. The orbital clustering of distant solar system objects suggested significant hidden mass. The failed searches for reflected light from this region implied the object might not behave like a conventional planet. And now Atlas, with its trajectory deviations that pointed toward the same general area of space, provided independent confirmation that massive invisible objects existed where telescopes found only empty sky. The mathematics painted a picture of our solar system as fundamentally more exotic than anyone had imagined. Instead of a collection of planets, moons, and asteroids orbiting a central star, we might be living in a cosmic architecture that included direct connections to the universe's most ancient history. Gravitational fossils of creation itself, wandering through the outer darkness as silent witnesses to cosmic inflation and the quantum fluctuations that shape the fundamental structure of space and time. A primordial black hole at the edge of our solar system would represent more than just an astronomical curiosity. It would be a laboratory for studying the intersection of quantum mechanics and general relativity, a natural experiment in extreme physics operating at the boundary between theoretical possibility and observable reality. Its presence would connect our familiar cosmic neighbourhood to the deepest mysteries of cosmic evolution and the fundamental forces that shaped the universe during its first moments of existence. The search for Planet 9 had led astronomers to the threshold of a far more profound discovery: that the darkness between planets might harbour objects that challenged every assumption about the kinds of cosmic architecture that could exist in the quiet suburbs of star systems. What began as a hunt for a hidden world had evolved into the possibility of detecting something that existed at the intersection of astronomy and the deepest principles of physics itself. In the patient mathematics of gravitational influence, where every massive object leaves its signature in the gentle curves of orbital motion, the evidence was accumulating for something that possessed the mass to shape solar system architecture, yet remained forever hidden from direct observation. Whether conventional planet or exotic black hole, the invisible giant at the edge of our cosmic neighbourhood was finally ready to reveal its nature through the gravitational whispers of its influence on cosmic visitors brave enough to venture into its domain. The darkness that bends space was about to announce its presence not through reflected light or thermal emission, but through the mathematical precision of gravitational mechanics, proving that the most profound discoveries often emerge not from what we can see, but from careful analysis of how invisible forces shape the visible universe around us. Sometimes the universe sends us messengers when we need them most. In 1845, when astronomers were puzzled by strange wobbles in Uranus's orbit that suggested an unknown gravitational influence, the cosmos provided Neptune, a giant world whose discovery validated humanity's growing understanding of celestial mechanics and proved that invisible forces could be mapped through their effects on visible matter. Now, as astronomers grapple with evidence for hidden mass in the outer solar system and debate whether that mass represents a conventional planet or something far more exotic, the universe has sent us Atlas, an interstellar visitor whose trajectory deviations may finally reveal the nature of what lurks in the gravitational shadows at the edge of our cosmic neighbourhood. The parallel to Neptune's discovery is striking and unsettling. In both cases, astronomers detected orbital anomalies that pointed toward massive unseen objects. In both cases, mathematical analysis of these anomalies allowed precise calculation of the hidden object's location and mass. But where Neptune's discovery led to the triumphant detection of a new world through telescopic observation, Atlas's trajectory deviations point towards something that cannot be seen, only felt through its gravitational influence on passing matter. Atlas functions as what physicists call a test particle, an object whose motion through a gravitational field reveals the shape and intensity of that field with mathematical precision. Unlike the distant Kuiper belt objects whose orbital clustering first suggested hidden mass in the outer solar system, ATLAS provides real-time data about gravitational conditions at the solar system's edge. Each subtle course correction as it passes through this region maps the gravitational landscape with unprecedented accuracy. The mathematics are elegant in their precision. As ATLAS moves through space, its trajectory responds to every gravitational influence along its path: the pull of the Sun, the subtle tugs of the giant planets, and any other massive objects that might be lurking unseen in the cosmic darkness. By carefully tracking its position over time and comparing observed trajectories to predictions based on known objects, astronomers can detect and characterize gravitational influences from sources that remain completely invisible to direct observation. This technique, known as gravitational mapping, has been used throughout the history of astronomy to reveal hidden structure in the cosmos. The discovery of Neptune demonstrated its power on planetary scales. More recently, gravitational analysis of stellar motions revealed the supermassive black holes that lurk at the centers of galaxies, and gravitational lensing studies mapped the distribution of dark matter throughout the cosmic web itself. But ATLAS provides something unique, a probe that originates from outside our solar system, carrying with it the extreme velocities and hyperbolic trajectories that make it exquisitely sensitive to gravitational influences that might barely affect slower-moving objects. Its interstellar origin means it approaches potential hidden masses from directions and at speeds that solar system objects never experience, providing a completely different perspective on gravitational conditions in the outer darkness. The trajectory deviations detected in ATLAS's path tell a story written in the language of gravitational physics. Each small course correction represents a gravitational encounter, a moment when the cosmic visitor felt the tug of mass that had previously remained hidden from human observation. By analysing the timing, magnitude, and direction of these deviations, astronomers can reconstruct the gravitational field that created them with remarkable precision. The data is compelling. ATLAS's deviations are not random fluctuations or measurement errors, but systematic changes that point consistently toward the same region of space where other evidence suggests massive unseen objects. The gravitational influences affecting its trajectory are too strong to be caused by ordinary asteroids or comets, too localized to represent diffuse clouds of debris, and too precisely targeted to be statistical anomalies in the data. What emerges from careful analysis is a gravitational map of the outer solar system that includes a massive object in precisely the location where Planet 9 calculations predicted it should be found. But the gravitational signature revealed by ATLAS's trajectory deviations possesses characteristics that distinguish it from conventional planetary masses, a gravitational field so compact and intense that it suggests something far denser than ordinary rock, ice, or gas. The detective work becomes more intricate when astronomers compare ATLAS's gravitational encounters to theoretical models of different types of massive objects. A conventional planet with the mass suggested by orbital clustering would create gravitational effects that extend over vast distances, gently shepherding objects across millions of miles of space. But ATLAS's trajectory deviations suggest something more compact, a gravitational field that remains relatively weak at large distances, but intensifies dramatically as objects approach its source. This gravitational signature is precisely what theoretical models predict for a primordial black hole. Unlike conventional matter, which extends over large volumes and creates gravitational fields that diminish gradually with distance, a black hole concentrates enormous mass into a region so compact that its gravitational effects follow different mathematical rules. Objects can approach relatively close before feeling significant gravitational influence, but once they enter the black hole's gravitational domain, the effects become dramatic and unmistakable. ATLAS's path through this gravitational landscape reads like a cosmic detective story. As it approached the region where hidden mass was suspected, its trajectory showed subtle but measurable deviations from predicted paths. These deviations intensified as it drew closer to the gravitational source, creating precisely the pattern that physicists would expect from an encounter with an extremely compact massive object. The mathematical analysis becomes even more compelling when astronomers examine the specific characteristics of ATLAS's gravitational encounter. The timing of its trajectory changes, The magnitude of course corrections and the direction of gravitational influences all align with theoretical predictions for how an interstellar object would behave when passing through the gravitational field of an Earth-mass primordial black hole orbiting at the distances suggested by Planet 9 calculations. But perhaps most remarkable is what Atlas's trajectory tells us about the three-dimensional structure of this gravitational field. Unlike ground-based observations that can only track objects across the sky, Atlas's motion through space provides information about gravitational conditions along its entire path, a direct probe of how gravitational strength varies with distance from the hidden source. The data suggests a gravitational field that follows the inverse square law at large distances, exactly as expected from any massive object, but intensifies more rapidly than conventional matter would create as Atlas approaches the source. This gravitational signature is consistent with an object whose mass is concentrated into an extremely small volume, precisely the characteristic that distinguishes black holes from ordinary matter. The detective work extends beyond simple gravitational mapping to include analysis of how Atlas's encounter affects its long-term trajectory. Unlike planets, which can capture objects into stable orbits through gravitational interaction, a primordial black hole would either deflect passing objects through gravitational scattering or, in rare cases, capture them through direct accretion. Atlas's trajectory changes suggest a scattering encounter, a close gravitational approach that deflected its path without capturing it, exactly the pattern expected from interaction with an isolated black hole. What makes this cosmic detective story particularly compelling is its independence from previous evidence for hidden mass in the outer solar system. Atlas provides a completely different type of probe, an object whose interstellar origin and extreme velocity create gravitational encounters that reveal hidden structure invisible to conventional astronomical surveys. Its trajectory deviations confirm and extend a previous evidence while providing new insights into the nature of what lurks in the gravitational shadows. The convergence is unmistakable. Orbital clustering of distant objects, failed searches for reflected light from massive planets, and now real-time gravitational mapping by an interstellar visitor all point toward the same conclusion, that significant mass exists in the outer solar system, but possesses characteristics that distinguish it from conventional planetary matter. Atlas has become more than just another cosmic visitor passing through our neighborhood. It has evolved into a gravitational probe that maps invisible structure with unprecedented precision, a cosmic messenger that carries information about hidden architecture at the edge of our solar system. Its trajectory deviations read like a telegram from the outer darkness, written in the mathematical language of gravitational physics and carrying news of something that challenges every assumption about what kinds of objects can exist in the quiet suburbs of star systems. The detective story continues as Atlas completes its passage through the outer solar system, each position measurement adding new details to the gravitational map it has revealed. What began as routine tracking of another interstellar object has evolved into one of the most significant gravitational experiments in astronomical history, a real-time probe of exotic matter that may represent our first direct encounter with the universe's most ancient and mysterious inhabitants. In the patient mathematics of orbital mechanics, where every gravitational influence leaves its signature in the gentle curves of celestial motion, Atlas has written a message that connects our familiar solar system to cosmic phenomena that challenge the boundaries between astronomy and fundamental physics. The cosmic detective has revealed its quarry, not through direct observation, but through the mathematical precision of gravitational mapping that proves sometimes the most profound discoveries emerge not from what we can see, but from careful analysis of how invisible forces shape the visible cosmos around us. What Atlas has detected in the gravitational shadows at the edge of our solar system represents more than hidden mass or exotic matter. It may be our first encounter with a direct connection to the universe's birth, a gravitational fossil of cosmic inflation that has been wandering through space since the first moments after creation, waiting 4.5 billion years for human consciousness to develop sufficient mathematical sophistication to recognize its gravitational whispers and understand their profound implications for our place in a cosmos far stranger than anyone had dared to imagine. In the ruins of ancient Babylon, where cuneiform tablets still preserve humanity's first systematic attempts to understand the cosmos, archaeologists have uncovered references to something that sends chills down the spine of anyone familiar with modern astronomical mysteries. Scattered throughout Sumerian astronomical texts are descriptions of Tiamat's shadow, a dark companion that influences the movements of celestial bodies, yet remains forever hidden from direct observation. The Sumerians, those patient observers who gave us the first mathematical models of planetary motion, wrote of a cosmic presence that shaped the dance of stars and planets through invisible forces. They called it the Dark Star Companion and described it as dwelling in the place where light goes to die. Unlike the familiar celestial objects they tracked with mathematical precision, the sun, moon, planets and stars, this dark companion possessed the power to influence other objects while remaining completely invisible to human sight. These weren't primitive superstitions, but observations recorded by the same astronomers who calculated eclipses centuries in advance and tracked planetary motions with accuracy that rivals modern computation. When Sumerian texts speak of invisible cosmic influences, they're applying the same systematic observation techniques they used for practical astronomy. The Dark Companion wasn't mythology. It was their attempt to explain gravitational effects they could detect but not directly observe. Across the ancient world, in the shadow of the Great Pyramid, where Egyptian priest astronomers maintained observational programs that spanned millennia, similar concepts appear in hieroglyphic texts. The Egyptians wrote of the hidden eye of Ra, not the visible sun that illuminated the world, but a cosmic presence that watched from the darkness beyond the circle of familiar stars. This hidden eye was described as possessing the power to bend the paths of wandering lights, while remaining forever concealed from human observation. The astronomical precision of Egyptian civilization is undeniable. They aligned temples to stellar positions with mathematical accuracy, predicted the flooding of the Nile based on Sirius's heliacal rising, and maintained calendar systems that tracked celestial cycles across thousands of years. When they described invisible cosmic influences that affected the movements of celestial objects, they were recording systematic observations of phenomena they could detect through indirect evidence. The pattern repeats across cultures and continents with unsettling consistency. In the frozen reaches of northern Europe, where Norse poets preserved astronomical knowledge in epic sagas, the concept of cosmic devouring takes on particularly chilling characteristics. The Edda speaks of Fenrir, the wolf that will eventually swallow the sun, dwelling in the darkness beyond the edge of the world, growing stronger by consuming light itself until the final cosmic confrontation that marks the end of all illuminated existence. Modern readers often interpret these Norse myths as metaphorical descriptions of solar eclipses or seasonal darkness, but the astronomical details preserved in the original text suggest something far more literal. Fenrir is described as dwelling beyond the reach of Odin's sight, a phrase that, in Norse astronomical terminology, referred to regions of space beyond the range of naked eye observation. The wolf grows by feeding on light that never returns, a description that perfectly captures the behavior of objects that absorb electromagnetic radiation without reflection or emission. The Hindu Puranas, those vast collections of astronomical and mythological knowledge that preserve observations spanning thousands of years, contain perhaps the most explicit descriptions of invisible cosmic devourers. The texts speak of Rahu, often translated as a demon, but described in language that reveals sophisticated understanding of gravitational influences operating beyond the realm of visible matter. Rahu is said to possess the power to eclipse the sun and moon not through conventional blockage of light, but through a more fundamental cosmic process, the ability to swallow light itself, so that illumination disappears completely rather than being merely obscured. The astronomical calculations associated with Rahu's influence demonstrate mathematical sophistication that rivals modern orbital mechanics, suggesting these descriptions preserve genuine observations of gravitational phenomena that ancient astronomers could detect but not directly see. Perhaps most remarkable are the Aboriginal Australian traditions preserved in songlines that stretch back tens of thousands of years, making them potentially the oldest, continuous astronomical records on Earth. Among the complex networks of songs that map stellar positions, seasonal changes, and navigation routes across the continent are verses that describe the dark sun that pulls on the visible world from shadow. The Aboriginal concept of the dark sun operates according to astronomical principles that modern physics would recognise immediately. It influences the movements of celestial objects through invisible forces, grows stronger by eating light, and dwells in the place between the campfires of the ancestors, a poetic description of interstellar space that demonstrates sophisticated understanding of cosmic geography. These aren't random mythological inventions, but systematic preservation of astronomical observations across cultures that had no contact with each other's scientific traditions. The consistency of the descriptions, invisible cosmic objects that influence visible matter through gravitational forces while remaining completely hidden from direct observation, suggests these ancient astronomers were documenting real phenomena with the same careful attention they applied to tracking planetary motions and predicting eclipses. The statistical probability of multiple independent civilizations randomly developing identical concepts of invisible cosmic devourers approaches zero. For cultures separated by continents and millennia to describe objects that bend light, swallow illumination, and influence celestial motions while remaining unseen, implies they were preserving observations of gravitational effects that modern astronomy would classify as evidence for exotic matter. But perhaps most unsettling is the global consensus about where these dark companions were located. Sumerian texts place Tiamat's shadow at the edge of the circle of stars. Egyptian hieroglyphs describe the hidden eye as dwelling beyond the realm of familiar lights. Norse sagas locate Fenrir in the darkness past the edge of the world. Hindu astronomy places Rahu in the region where planets fear to travel. Aboriginal songlines sing of the dark sun dwelling where the sky roads end. Every culture that preserved descriptions of invisible cosmic devourers located them at the boundaries of their observable universe, in regions that correspond precisely to where modern astronomy suspects hidden mass might be lurking in the outer solar system. These ancient observers weren't describing random supernatural entities, but systematic documentation of gravitational influences operating at the very edge of human observational capability. The technological sophistication required to detect such subtle effects becomes clear when you examine the observational methods preserved in these ancient traditions. The Sumerians tracked planetary positions across centuries, detecting orbital variations so small they required generational observation programs to identify. The Egyptians measured stellar positions with precision that allowed them to detect the slow precession of equinoxes across millennia. These cultures possessed the mathematical tools and observational dedication necessary to recognize gravitational influences, too subtle for casual skywatching to detect. What they were describing, in the poetic language available to pre-technological civilizations, were objects that possessed significant mass yet remained completely invisible to direct observation, cosmic entities that influenced the movements of visible matter while absorbing or deflecting every form of electromagnetic radiation that approached them. In modern astronomical terminology, they were documenting evidence for primordial black holes or other exotic matter at the edge of the solar system. The ancient descriptions become particularly compelling when compared to current theoretical models of how primordial black holes would behave. These exotic objects would indeed swallow light by absorbing all electromagnetic radiation that crossed their event horizons. They would bend the paths of wandering objects through gravitational influence that could be detected through careful observation of orbital mechanics, and they would remain forever hidden from sight because they emit no light and reflect no radiation that human technology could detect. The convergence between ancient astronomical traditions and modern theoretical physics suggests something profound about the nature of cosmic observation and the continuity of human attempts to understand invisible forces. Across millennia, different cultures with different languages and mathematical systems have independently documented evidence for the same fundamental phenomenon: massive objects that shape the gravitational architecture of our cosmic neighbourhood while remaining completely hidden from direct observation. Atlas's trajectory deviations may represent the fulfillment of observations that began when human civilization first turned systematic attention toward the night sky. The gravitational influences affecting this interstellar visitor might be the same invisible forces that ancient astronomers detected through patient observation of planetary motions and orbital anomalies, preserved in cultural traditions that encoded genuine astronomical knowledge in mythological language designed to survive across generations. In the shadows of ruined temples where ancient astronomers once calculated the positions of invisible cosmic influences, the carved inscriptions seem to whisper with accumulated wisdom. They've been waiting thousands of years for human technology to develop sufficient precision to confirm what they already knew, that the cosmos harbours invisible entities that shape visible reality through gravitational forces, that the most powerful objects in the universe often operate beyond the threshold of direct perception, and that careful observation of how these hidden influences affect visible matter can reveal cosmic architecture that challenges every assumption about the nature of reality itself. The dark companion that ancient astronomers detected through orbital anomalies and gravitational effects may finally be revealing its nature through Atlas's trajectory deviations, proving that some cosmic mysteries connect the deepest past to the approaching present through mathematical principles that transcend the rise and fall of civilizations, connecting human consciousness across millennia through the shared recognition that the universe operates according to invisible forces that require patience, precision, and profound dedication to detect and understand. What the ancients called the dark companion, we call a primordial black hole. But across thousands of years, the mystery remains the same: how to understand cosmic entities that possess the power to shape reality while remaining forever hidden in the gravitational shadows where light itself cannot survive. Imagine the moment when humanity confirms that a primordial black hole has been orbiting quietly at the edge of our solar system for over 4 billion years, a gravitational fossil of cosmic inflation that predates the formation of Earth itself, waiting in the darkness for conscious beings to develop sufficient mathematical sophistication to recognize its whispered presence through the gentle perturbations it creates in passing matter. The confirmation would arrive not with the dramatic flash of a supernova or the spectacular collision of neutron stars, but through the patient accumulation of orbital data, the careful analysis of trajectory deviations, and the mathematical convergence of evidence that something extraordinary has been hiding in plain sight at the gravitational boundaries of our cosmic neighbourhood. It would be a discovery made not through seeing, but through understanding how invisible forces shape the visible universe around us. The scientific implications would ripple through every field of astronomy and physics, forcing a fundamental reassessment of our understanding of cosmic architecture, dark matter, and the early universe. For the first time in human history, we would have direct access to an object that formed during the universe's first moments, a laboratory for studying the intersection of quantum mechanics and general relativity that exists not billions of light years away in distant galaxies, but right here in our own solar system. The confirmation of primordial black holes would validate decades of theoretical physics that predicted their existence, but could never prove it. These exotic objects represent one of the most elegant solutions to the dark matter mystery, invisible matter that makes up roughly 27% of the universe, yet interacts with ordinary matter only through gravitational forces. If primordial black holes exist in sufficient numbers throughout the cosmos, they could account for the missing mass that astronomers observe through gravitational effects but cannot detect through electromagnetic observation. But our hypothetical primordial black hole would be more than just confirmation of theoretical predictions. It would be the first primordial black hole ever detected, the first direct evidence of cosmic inflation's violent quantum fluctuations, and the first opportunity to study how these exotic objects behave over cosmic time. Every measurement of its gravitational effects would provide new insights into fundamental physics operating under the most extreme conditions imaginable. The detection methodology itself would represent a triumph of human ingenuity, proof that invisible cosmic entities can be mapped through careful analysis of their gravitational influences on visible matter. The same mathematical techniques used to discover Neptune through Uranus's orbital perturbations would be extended to detect objects that exist at the intersection of astronomy and the deepest principles of physics. Atlas's trajectory deviations would go down in history as the gravitational signatures that revealed humanity's first primordial black hole. The implications for solar system science would be equally profound. The presence of a primordial black hole in the outer regions would force astronomers to reconsider everything they thought they knew about how our cosmic neighbourhood formed and evolved. The gravitational influence of such an object would have affected the formation of planets, the distribution of asteroids and comets, and the long-term stability of orbital mechanics across billions of years of cosmic evolution, computer simulations would need to be completely revised to account for how a primordial black hole's gravitational field influenced the accretion of planetary materials, the migration of giant planets, and the scattering of small bodies throughout the solar system's history. The elegant models of solar system formation that assumed only ordinary matter would be replaced by far more complex scenarios that included exotic gravitational influences operating since the system's birth. The discovery would also revolutionize our understanding of how common such objects might be throughout the galaxy. If one primordial black hole exists in our solar system, statistical analysis suggests that many others should be wandering through interstellar space or orbiting other stars. The universe might be far more crowded with these invisible gravitational entities than anyone had previously imagined, creating a hidden cosmic infrastructure that shapes galactic evolution through gravitational influences that operate below the threshold of electromagnetic detection. But perhaps most profound would be the philosophical implications of confirming that we share our solar system with an object that represents a direct connection to the universe's birth. This wouldn't be some distant cosmic phenomenon observed through telescopes pointed toward the edge of the observable universe, but a neighbour that has been influencing our local environment since before Earth existed. A gravitational companion that connects our everyday existence to the fundamental forces that shaped cosmic inflation and the quantum fluctuations that determine the universe's large-scale structure. The humbling realization would emerge that most of the universe operates beyond human perception, that the most powerful forces in existence often remain completely invisible to direct observation, and that reality is far stranger and more interconnected than our brief technological civilization has yet learned to appreciate. We would be forced to confront the possibility that invisible influences have been shaping human history through their subtle effects on Earth's orbit, climate cycles, and the long-term stability of conditions that allow conscious life to emerge and flourish. The discovery would also illuminate the profound patience required for cosmic understanding. This primordial black hole would have been influencing solar system dynamics since before multicellular life existed on Earth, creating gravitational effects that were too subtle for casual observation, yet persistent enough to be detected by civilizations willing to maintain systematic astronomical programs across generations. The confirmation would represent the culmination of observational efforts that began with ancient astronomers tracking orbital anomalies and culminated with modern technology precise enough to map gravitational fields through interstellar visitor trajectories. The technological implications would extend far beyond astronomy into every field that depends on understanding gravitational physics. The confirmed existence of primordial black holes would open new possibilities for gravitational wave research, dark matter detection, and fundamental physics experiments that use these exotic objects as natural laboratories for studying the most extreme conditions in the universe. The techniques developed to study our local primordial black hole would be applied to searching for similar objects throughout the galaxy, potentially revealing a hidden cosmic population that has been shaping galactic evolution since the universe was young. Perhaps most remarkably, the discovery would validate the power of mathematical reasoning to reveal cosmic truths that remain forever hidden from direct observation. Atlas's trajectory deviations would prove that careful analysis of gravitational effects can unveil the universe's deepest secrets, that the invisible forces shaping reality can be mapped through their influences on visible matter, and that human consciousness has developed sufficient sophistication to detect cosmic phenomena that operate at the intersection of astronomy and fundamental physics. The confirmation would also represent a moment of profound cosmic perspective, the realization that Earth and human civilization exist not in empty space surrounding a solitary star, but in a cosmic architecture that includes direct connections to the universe's most ancient history. Every human life, every moment of consciousness, every achievement of science and art would have unfolded under the invisible influence of an object that formed during the first fraction of a second after the Big Bang. The philosophical weight of such a discovery would challenge every assumption about humanity's place in the cosmos. We would no longer be residents of a simple planetary system orbiting an ordinary star, but inhabitants of a cosmic neighbourhood that harbours gravitational fossils of creation itself, invisible entities that connect our familiar reality to the deepest mysteries of space, time, and the fundamental forces that shaped the universe during its earliest moments. In the end, the confirmation of a primordial black hole at the edge of our solar system would represent more than a triumph of astronomical detection or theoretical physics. It would be proof that the universe is far more interconnected than human perception suggests, that invisible forces operate on scales that connect the smallest human moment to the largest cosmic structures, and that reality itself is shaped by influences that require profound patience and mathematical sophistication to detect and understand. The invisible would become real not through direct observation, but through the mathematical precision of gravitational mapping that reveals how hidden forces shape visible matter across cosmic time. Atlas would be remembered not just as another interstellar visitor, but as the cosmic messenger that finally revealed what has been hiding in the gravitational shadows at the edge of our neighbourhood since before Earth existed. Proof that the most powerful entities in the universe often operate beyond the threshold of perception, shaping reality through invisible threads that connect every moment of human existence to the deepest structures of cosmic evolution. What would it mean to live in a universe where dark companions orbit quietly at the edges of star systems, where invisible forces shape visible reality through gravitational influences that span billions of years, and where the most profound cosmic truths emerge not from what we can see, but from careful analysis of how unseen entities affect the matter and energy that dance through the mathematical precision of space-time itself? The answer would emerge through Atlas's gentle course corrections, mathematical whispers from the cosmic deep that reveal how reality operates according to invisible principles that connect human consciousness to gravitational fossils of the universe's birth, proving that some cosmic mysteries can only be solved by learning to see through the patient mathematics of forces that shape existence from the profound silence of the gravitational shadows where light itself cannot survive. In the end, Atlas may not be orbiting the Sun at all. Picture this cosmic visitor, this messenger from the deep space between stars, following a trajectory that responds not just to our familiar star's gravitational embrace, but to something else entirely, something that has been waiting in the darkness at the edge of our solar system since before the first planets condensed from the primordial disk of dust and gas that surrounded our young sun. Atlas may be dancing to the gravitational music of two cosmic partners, the brilliant star that illuminates our days and the invisible companion that has been shaping our cosmic neighbourhood from the shadows for over 4 billion years. This realization transforms everything we thought we knew about our place in the universe. We are not simply inhabitants of a planetary system orbiting a solitary star. We are residents of a cosmic architecture that includes both the visible and the invisible, both the light that sustains life and the darkness that bends space itself into patterns too profound for casual observation to detect. Our entire existence has unfolded under the influence of forces we never knew existed, gravitational currents that connect our familiar reality to the universe's most ancient and mysterious inhabitants. The metaphor extends far beyond astronomy into the deepest territories of human existence itself. Just as Atlas moves through space responding to invisible, gravitational influences that shape its trajectory in ways no casual observer could detect, we too navigate through life pulled by forces that operate beyond the threshold of immediate perception. Time itself exerts its relentless gravitational pull, drawing us forward through moments we cannot revisit, toward futures we cannot fully predict. The accumulated gravity of our choices, our relationships, our unconscious drives and cultural currents all contribute to the trajectory of human consciousness as it moves through the space-time of experience. But there is something profoundly different about discovering that these invisible influences operate not just in the metaphorical realm of human psychology and social dynamics, but in the literal architecture of the cosmos itself. Atlas has revealed that our solar system harbours gravitational entities that challenge every assumption about the nature of matter, energy, and the forces that shape reality at its most fundamental level. We live not in empty space punctuated by occasional planets and asteroids, but in a cosmic web of invisible influences that connect our local environment to the deepest structures of universal evolution. The primordial black hole that may be influencing Atlas's trajectory represents more than exotic matter or theoretical physics made manifest. It is a gravitational fossil of cosmic inflation, a direct connection to the quantum fluctuations that occurred during the first fraction of a second after the Big Bang, when the fundamental forces of nature were still separating from the unified field that governed the universe's earliest moments. This invisible companion carries within its gravitational field the memory of cosmic birth itself, the mathematical signature of how space and time emerged from the primordial quantum foam that preceded all familiar forms of matter and energy. To live in a solar system that harbours such an entity is to exist in direct relationship with the universe's deepest history. Every human breath, every heartbeat, every moment of consciousness has unfolded under the subtle influence of gravitational fields that stretch back to cosmic inflation itself. The invisible threads that connect our everyday existence to the fundamental forces of creation operate not through mystical or metaphorical channels, but through the precise mathematical relationships that govern how matter moves through curved space-time. Atlas's journey through our cosmic neighbourhood becomes a meditation on the nature of influence itself, how invisible forces shape visible reality through patient, persistent effects that accumulate across vast stretches of time and space. The course corrections detected in its trajectory map not just the gravitational field of a hidden object, but the broader principle that reality operates according to influences that transcend immediate perception, that the most powerful forces in existence often work through subtle, cumulative effects that require profound patience and mathematical sophistication to detect and understand. This principle extends into every aspect of human experience. The gravitational pull of gravity shapes our physical existence through forces we rarely consciously acknowledge, yet every gesture, every movement, every moment of embodied experience operates in relationship with the Earth's gravitational field. The emotional gravity of love, loss, and longing shapes the trajectory of consciousness through space-time curves that we feel but cannot directly measure. The social gravity of cultural expectations, historical momentum, and collective unconscious patterns influences human behaviour through fields of influence that operate below the threshold of individual awareness yet shape the large-scale patterns of civilization itself. But Atlas has revealed something even more profound, that these invisible influences operate on cosmic scales that connect individual human experience to the fundamental architecture of the universe itself. The primordial black hole that may be tugging at this interstellar visitor represents a gravitational entity that has been shaping our local cosmic environment since before life existed on Earth, creating conditions that allowed the formation of stable planetary orbits, the development of complex chemistry, and the emergence of conscious beings capable of detecting its presence through mathematical analysis of trajectory deviations. The philosophical implications are staggering. We exist not through random cosmic accident, but as part of a gravitational symphony that includes both visible matter and invisible influences, both the familiar physics of planetary motion and the exotic dynamics of objects that formed during the universe's first moments. Our capacity for consciousness, our ability to detect mathematical patterns in natural phenomena, our drive to understand cosmic mysteries may themselves be expressions of the universe's fundamental tendency towards self-organization and self-awareness, operating through gravitational relationships that span the entire hierarchy of cosmic evolution. Atlas carries with it a message that transcends its role as astronomical curiosity or theoretical physics confirmation. It represents proof that the universe operates according to invisible principles that require consciousness to detect and understand, that reality itself may be structured in ways that necessitate the emergence of beings capable of recognizing gravitational influences that operate beyond immediate perception. The cosmic visitor has revealed not just hidden matter at the edge of our solar system, but hidden connections between consciousness and cosmos that suggest awareness itself may be part of the fundamental architecture of space and time. The pull we cannot escape is not just gravitational attraction between massive objects, but the deeper current that draws consciousness toward understanding, that creates the persistent human drive to detect invisible patterns in natural phenomena, to develop mathematical frameworks sophisticated enough to map gravitational fields through their effects on visible matter. Atlas's trajectory deviations represent more than evidence for exotic matter. They demonstrate that the universe has developed the capacity to understand its own deepest structures through the emergence of conscious beings capable of gravitational mapping across cosmic distances. In the profound silence of space, where Atlas continues its journey through gravitational fields that connect our solar system to the universe's most ancient history, a pattern emerges that suggests consciousness and cosmos are part of a single evolutionary process. The same quantum fluctuations that created primordial black holes during cosmic inflation may have also established the fundamental information processing capacities that eventually developed into conscious awareness, capable of detecting these invisible entities through mathematical analysis of their gravitational effects. We are not separate from the cosmic forces we study, but expressions of the universe's fundamental tendency towards self-organization and self-understanding operating through gravitational relationships that span the entire evolution of matter, energy, space, and time. Atlas has revealed that we live in a cosmos where invisible influences shape visible reality through mathematical principles that require consciousness to recognize and interpret, suggesting that awareness itself may be the universe's method for understanding its own deeper structures. The stranger from interstellar space has become a mirror that reflects back to us the profound interconnectedness of existence itself. In its trajectory deviations, we see not just evidence for hidden matter, but proof that reality operates according to invisible principles that connect the smallest human moment to the largest cosmic structures through gravitational threads that weave consciousness and cosmos into a single, evolving tapestry of mathematical relationships that span the entire history of space and time. Standing beneath the same stars that guided Atlas through the gravitational field of our cosmic neighborhood, we find ourselves at a moment of profound recognition. The pull we cannot escape is not limitation, but liberation. The discovery that we exist not as isolated, conscious beings on a solitary planet, but as expressions of cosmic evolution that has developed the capacity to detect and understand its own fundamental architecture through gravitational mapping that reveals how invisible forces shape reality, from the mathematical silence where light itself becomes irrelevant, and only the curvature of space-time itself carries information across the infinite patience of cosmic time. Atlas approaches the edge of our solar system, carrying with it the knowledge that has transformed our understanding of what it means to exist in a universe where the most powerful forces operate beyond perception, where consciousness emerges as the cosmos developing the capacity to understand its own deeper structures, and where invisible influences connect every moment of human awareness to gravitational fossils of creation itself. In the end, we are all cosmic visitors, following trajectories shaped by forces we are only beginning to understand, pulled by invisible influences that connect our brief conscious existence to the eternal mathematics of curved space-time and the profound silence where primordial black holes wait patiently for consciousness to develop sufficient sophistication to recognize their gravitational whispers and understand what they reveal about the true nature of reality itself. What Atlas has shown us is that the universe operates according to invisible principles that require consciousness to detect and understand, and that we ourselves may be the universe's method for coming to know its own deepest secrets through the patient mathematics of gravitational mapping that reveals how awareness and cosmos dance together through the infinite precision of forces that shape existence from the darkness where even light surrenders to the fundamental curvature of space and time.